All right, so welcome back to the deep dive. Today, we're diving into something that's super useful, especially if you're aiming for those senior software engineer roles.
Oh, yeah.
We're talking about understanding and using simple languages like right inside your software.
Interesting.
It's one of those skills that can really make a difference.
Definitely.
Not just for tricky problems, in specific areas, but also for those tough technical interviews.
Oh, absolutely. When you start moving up, you'll see that being able to express a problem in a really clear way, almost like using a language.
Right.
And then actually designing a system that can understand and work with that language. It's a big deal. It's like a level up for how you solve problems.
It is, and that's where this really cool design pattern comes in, the interpreter pattern.
Yeah.
Now, don't worry, it sounds fancy, but we're not going full on building a Python interpreter or anything.
Right, right.
It's more about making mini languages for specific things you need to do.
Exactly. It's about taking a set of rules, like a grammar, and creating something that can take sentences written with those rules and actually do something useful with them.
I like that.
We'll break it down, see what's good about it, and also when it might not be the best choice.
Perfect.
Yeah.
And we'll even look at real examples. Think about controlling simulated ducks with commands like, right, while daylight fly, quack.
Okay.
We'll also connect this to stuff you might already know, like how regular expressions work or even how Boolean logic is handled.
By the end, you'll know when and how to use the interpreter pattern. It's really neat for some problems.
Absolutely.
And definitely something you'd want to be able to talk about in a technical interview.
That's it. So let's dive in. What's the big idea behind the interpreter pattern?
Well, at its heart, the interpreter pattern is about defining a grammar for a language and then building an interpreter that can handle statements written in that language.
Okay.
It's all about taking problems that you can describe with a simple language.
Right.
And then creating an interpreter to understand and run those expressions to solve the problem.
That makes a lot of sense. So instead of writing a different solution for every little variation of a problem, we come up with this small specific language to describe it.
Right.
And then the interpreter takes care of actually solving it based on that description.
Exactly. Think about regular expressions, for example. Instead of writing a whole new algorithm each time you need to check if a string matches a pattern, you just define the pattern using the language of regular expressions.
Makes sense.
Then, a regex engine, which often uses ideas similar to the interpreter pattern inside, interprets that expression to do the matching for you.
Okay, so we have this idea of a language.
Right.
What makes up this language? What tells us what's allowed and what's not?
The key is the grammar. It's like the rule book for the language, defining all the right ways to build sentences or expressions. And what's neat is that the interpreter pattern uses classes to represent each of these rules.
Let's go back to those ducks. What would a simple grammar look like if we wanted to tell our simulated ducks what to do?
Okay, so a very basic grammar could say that an expression can be a single command.
Okay.
Or a bunch of expressions in a row.
Got it.
Or even an expression that repeats. And then a command could be something simple like write, quack, or fly.
Right.
A sequence might be several expressions with semicolons between them. And a repetition could be like, while something is true, do this expression.
Okay, I'm starting to get it. So how do we go from this abstract grammar, these rules on paper, to something we can actually use in code?
This is where the interpreter pattern really shines. Basically, for every rule in our grammar, we create a class.
Okay.
So for our simple duck language, we might have an abstract base class called expression.
Right.
And then more specific subclasses like sequence for a series of actions,
Right.
repetition for repeating actions, and then actual command classes like write command, quack command, and fly command. See the connection? The write command becomes the write command class, quack becomes quack command, and so on. It's a straight mapping from the idea to the code.
Yeah, that's neat. And what about regular expressions? You mentioned their grammar is a bit more
complex.
Yeah, complex. How would that work with classes?
It's the same idea, even though it's more involved.
Okay.
You might define an expression as a single character, like A or B.
Right.
Or a sequence, like A. Or a repetition, like A. Or even a part in parentheses to group things together.
Okay.
And this grammar would then map to an abstract regular expression class with subclasses like literal expression, alternation expression, sequence expression, and repetition expression.
Wow.
Each representing a different part of the grammar.
All right, so we've got how the grammar is defined and how those rules become classes in code.
Yes.
Now, if we have an actual sentence in our language,
Okay.
let's say for the ducks, it's write, fly, quack.
Sure.
How does the interpreter actually work with this? How does it understand what we want the duck to do?
So every sentence or expression we have gets turned into what's called an abstract syntax tree, or AST.
Right. AST.
Yeah, think of it like a structured version of the sentence.
Yeah.
Built with the classes we just talked about.
Yeah.
The way the tree is organized directly reflects the grammar of the sentence.
Yeah.
It breaks down the sequence of characters into something meaningful and nested.
Can we see an example? Let's use that regular expression you mentioned earlier, raining and dogs, cats.
Sure.
How would that look as an AST?
Okay, picture the top of the tree being a sequence expression.
Right.
This is because we have raining and then the whole dogs, cats part.
Got it.
The first part of the sequence would be a literal expression for raining.
Okay.
The second part would be a repetition expression because of the may
Right.
and what's being repeated.
Well.
It's the group, dogs, cats,
Mm-hmm.
which would be an alternation expression in our tree, meaning or. And lastly, this alternation expression would have two literal expression objects underneath it. One for dogs and another for cats.
So the interpreter takes our sentence and kind of parses it into this tree, right? Where each part of the tree matches a rule from our grammar and represents a piece of the whole expression.
Exactly. That object diagram really helps to visualize this. You'd have a sequence expression at the top with branches going to a literal expression for raining on one side and a repetition expression on the other. And then that repetition expression would lead to an alternation expression, which finally splits into the dogs and cats literal expression objects.
Okay, now that we have this AST, how does the interpreter actually do something with it?
Right. This is where interpret comes in, right?
Yeah.
Each class in our abstract syntax tree, whether it's a literal expression, a sequence expression, or a command like quack command, has this interpret thing.
Right.
It's what makes each part of the tree do a specific thing, act or figure out its value.
And what about the context object that often goes with this interpret method?
Good point. The context is like a shared space that holds information that's important for the whole interpretation process. Think of it like the interpreter's workspace. If we're interpreting our duck commands, the context might hold the current state of the duck where it is, whether it's daytime and so on.
Okay, I see.
For a regular expression interpreter, the context would likely have the input string we're trying to match and maybe info about how much of that string has been processed or any captured groups.
So the interpret method of each node in the AST uses this context to know what to do or what value to give, right?
Exactly. Let's look at some examples. For a literal expression in a regex interpreter, its interpret method would probably check if the current part of the input string matches the literal it represents.
Right.
If it matches, it might update the context to show that those characters have been used.
Okay, what about our alternation expression, like the dogs, cats part?
Oh yeah, the interpret for that would try using interpret on each of its alternatives, the dogs and cats literal expression, with the current context.
Right.
If at least one of them works, meaning it finds a match in the input, then the whole alternation expression is considered successful.
Makes sense. And what about a repetition expression like that? That means 0 or more.
For that, the interpret would keep trying to use interpret on the expression it contains, the dogs, cats in our case.
Right.
It does this as many times as possible, as long as it finds a match in the input within the current context.
Yeah.
It keeps going until the inner expression doesn't match anymore.
Okay. And for a sequence expression where we have raining and then that repetition.
The interpret for that would simply run interpret on its first part, raining.
Right.
And then if that works, it would call interpret on the second part, the repetition, maybe updating the context as it goes.
Right.
Now, thinking about our ducks again, for a command like quack command, interpret would actually make the action happen. It would likely interact with a simulation, which would be stored in the context, to make the duck quack.
So each node in the AST knows how to evaluate itself based on what type it is and the overall state in the context, right?
Yes, exactly. To interpret the whole sentence, you start at the top of the abstract syntax tree and go down, calling interpret on each node. Every node does its part, maybe changing the context, and the final result is what you get from all these individual interpretations.
Okay, we've talked about the main idea, the grammar, the AST, and the important interpret part.
Yes.
Now, let's zoom out a bit and look at the bigger picture. What are the usual parts of the interpreter pattern?
So there are a few key players here.
Okay.
First, we have the client. This is the part that builds or receives the abstract syntax tree.
Right.
The client then works with the context, which we talked about, and the abstract expression. The abstract expression is usually an interface or abstract class that defines the interpret context method, which is the common starting point for all expressions in our language.
And then we have the actual implementations of these expressions.
Exactly. These are divided into two main types: terminal expression and non-terminal expression.
Okay.
A terminal expression is like the most basic building block of our grammar. They're the leaves of our abstract syntax tree.
Okay.
In our regular expression example, a literal expression would be a terminal expression.
Right.
It handles the basic symbols.
Now, what about non-terminal expression?
Those represent the more complex rules, the branches of the AST that connect terminals and other non-terminals.
Okay.
Classes like sequence expression, repetition expression, or alternation expression are all non-terminal expressions. They also have the interpret method.
Right.
But their job is usually to call interpret on the expressions they contain. They basically tell us how to interpret combinations of other expressions based on the grammar rules.
So the client builds this tree of terminal and non-terminal expression objects, and they all follow the abstract expression interface and know how to interpret themselves using the context.
Yes, that's a great summary of how it all works.
Right, so why go through all this trouble with grammars, classes, ASTs, and interpret? What are the real benefits of using the interpreter pattern?
It has some great advantages.
Okay.
First, it makes it super easy to change and expand the language. Since each rule is in its own class, you can use inheritance to modify existing rules or add new ones without messing up the rest of the system.
Okay.
It's very flexible.
That sounds great for keeping things up to date and adding features.
It is. Second, putting the grammar into code becomes pretty simple and systematic.
Really?
Because the classes for the grammar rules have a similar structure. They all have interpret.
Right.
And the development is pretty standardized. Sometimes you can even automate creating these classes using special tools if you have a formal grammar definition.
And what if we want to do more than just interpret the language, like analyze it or change it somehow?
That's another great thing.
Okay.
By adding new methods to our classes, the terminal expression and non-terminal expression ones,
Okay.
we can add new behaviors beyond just interpretation. For example, you could add a way to pretty print the abstract syntax tree back into something that's easy to read.
Right.
That would be helpful for debugging. Or you could add more complex validation or type checking right into these classes. And if you need to do lots of different things with the AST, the visitor pattern can be a lifesaver.
Okay.
It lets you define separate visitor classes for each task, so your grammar classes stay focused on the language structure.
Those are some good reasons to use this pattern, but like anything, there must be some drawbacks or times when it's not the best choice.
Right.
When should we avoid the interpreter pattern?
You're right, there are downsides.
Okay.
A big one is that if the grammar gets really complicated with tons of rules, you end up with a huge class hierarchy that's hard to manage. It can become overwhelming, so watch out for that complexity.
That makes sense. More rules mean more classes.
Exactly. And another thing is that performance might not be great, especially with complex languages or lots of input.
Okay.
Directly interpreting the abstract syntax tree can sometimes be slower than using more traditional parser or compiler generators.
So for really big, complicated languages,
Yeah,
a parser generator that makes optimized bytecode would be better.
most likely yes. If you're working with a full-on programming language, something like ANTLR or YAC is probably a better and faster way to go. The interpreter pattern is best for simpler, more specific languages where the grammar isn't too crazy.
You mentioned earlier that the interpreter pattern doesn't tell us how to create the abstract syntax tree in the first place.
Right.
Can you talk about that a bit more?
Sure. The focus is on representing the grammar and interpreting the AST.
Right.
Turning the raw input into the AST, that's the parsing part, is a separate thing. You can make the AST in different ways, like with a recursive descent parser or a table-driven parser from a parser generator. The interpreter pattern just takes this finished AST and starts interpreting it.
And you also mentioned the visitor and flyweight patterns briefly.
Oh, yeah,
Can you explain why they're useful with the interpreter pattern?
definitely. We touched on the visitor pattern earlier. It's really handy when you need to do lots of different things with the AST.
Yeah.
Instead of putting all those actions as methods in every single expression class,
Right.
which would make them really messy.
Yeah.
You can have separate visitor classes.
Mm.
Each visitor does one specific thing, like type checking or code generation.
Okay.
Then your expression classes just let the visitor in and let it do its thing on the tree.
Right, right.
This helps to separate the structure of your language from how you might want to process it. Now, the flyweight pattern is useful when you have lots of repeated terminal symbols, like variable names in code, or the same literal strings over and over.
Okay.
Making a new object every time for these repeated things in your AST can use a lot of memory.
Right.
The flyweight pattern lets you share these common symbols so you only have one copy of each, and different parts of the AST can use it.
That's pretty clever.
It's a good way to save memory in some cases.
We've been talking about examples like ducks and regular expressions. Are there any real systems out there that actually use the interpreter pattern?
Oh, definitely. Some compilers, like some Smalltalk compilers, have used it for parts of their language processing.
Okay.
SpecTalk, which is a system for handling different input file formats, is another example.
Mm-hmm.
And the QOCA Constraint Solving Toolkit uses it too.
So it's a pattern used in real situations where you need to understand a specific language.
Exactly. More broadly, you could say that any use of the composite pattern where the classes are designed to represent a language is like the interpreter pattern,
Right.
especially if there's an interpret method or something similar.
Mm.
It's about whether those classes are both defining and interpreting a language, even a very specific one.
This has been a really interesting deep dive into the interpreter pattern.
It has.
It seems really useful for certain problems, like when you need to create and understand a simple language within a bigger system.
It definitely is. It provides a structured and flexible way to interpret languages
Yeah.
by connecting the grammar rules directly to the code and using an abstract syntax tree to represent the input in a way that can be evaluated effectively.
Right.
The benefits of clear design, easy expansion of the language, and straightforward implementation for simpler grammars make it a valuable tool to have.
But as we've said, we need to remember the potential downsides,
Yeah.
especially when the grammar gets really complex and we have tons of classes, or when performance becomes an issue compared to other parsing methods.
Exactly. Knowing when to use and when not to use the interpreter pattern is really important for making good design decisions. For simpler languages, where the grammar is manageable and flexibility and a clear implementation are priorities, the interpreter pattern can be a really elegant and effective solution.
So, as you're out there, maybe even preparing for those senior level technical interviews,
Yeah.
where system design and design patterns are key, I'd like you to think about this. Are there any problems you run into a lot in your work or in system design? Could defining a simple language and building an interpreter be a good way to simplify things or make them more adaptable to changes in the future?
Good question.
Could this be a more organized and maintainable way to handle complex input formats instead of ad hoc solutions? It's worth thinking about as you consider different design choices.
That's a great point to end on. Understanding the interpreter pattern well gives you another way to look at tricky problems and work with language-like structures in your code.
I agree.
And that's something that really shows you're well-rounded and thoughtful senior software engineer.
Absolutely.
It's a valuable skill.
It is.
Okay.
All right. Thanks for joining us for another deep dive. We'll see you next time.
See you.